Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, with our ongoing series on networks and graphs, today we will be talking on random networks and graphs, and for this very discussion we have once again with us in our studios Dr. Aditya Sinha. Dr. Aditya Sinha is assistant professor in one of the leading institutions. Dr. Sinha has immense experience and knowledge. Hope her experience would definitely help us in understanding the topic in detail, that is random networks and graphs. So let's welcome our guest, Dr. Aditya Sinha. Dr. Sinha, welcome to the UGC lecture.
Thank you very much. Welcome viewers. In today's lecture on random graphs in network, we are mainly going to focus on the complex graphs like hypergraphs, multigraphs, and the graphs that are randomly generated. Means that we might have number of series of nodes, but how these nodes are connected to each other, the link formation, this is entirely random. So these are the main topic for our lecture. Before we start with the complex graphs, we revisit centrality measures, and there are two more important measures that we were continuing our discussion on. Information centrality and cross-clique centrality. In information centrality, what happens? A node I is like it might be important to a particular graph. So that particular node I may have some centrality in terms of degree, reachability, that is closeness, or decay, etc. Now, if this node is removed from the graph, what impact it will put on the entire network? This is what information centrality is, because we go by the conception, the very general basic conception that information travels in any graph, be it a technological graph or communication graph or any kind of graph, that information or any message that is being traveled would take a shortest path. And if a node with a high central value, with a like a very important position in the network, if that particular node gets removed, then what happens to the information that is being reached from a particular source to destination? Okay, so here information centrality is nothing but it's just a relative drop. It's a measure of the relative drop in the network efficiency that is caused by removal of edges incident on that particular node I for a specific graph, say for example G. Okay, so this is given by this formula. It's a relative measure. So first we find out the information centrality of the entire network, because this is the only centrality that consists of the entire network apart from the node. Okay, so here what happens? First we take the information centrality of the entire graph, and then we calculate the same measurement without the node I for which we are interested on, to find the impact of that node on the graph. Okay, and then it's divided by the whole graph centrality, and whatever measure we get will give the value of what is the drop in coverage of information, that is the information. And now if it get traversed from a particular station to another, then what is the drop in the coverage. Okay, so in our previous example, we can see that the coverage drop comes to 40%. Okay, so we take one more example over here. It will clarify the entire thing. Say we have this particular graph, a very simple one, over 5 vertices, right? And say we are interested to find the node impact of node 2 if it gets eradicated from the graph, then what happens to the connectivity thing. Okay, so what we did is first we have found out the entire list of ratio that you can see in the column that is specified by G. Okay, so from this we get that the normal information centrality of this particular graph G is 0.355. Okay, now what we do is we are interested to find out the node 2's impact. So by removing 2, that is from the node set of the graph G, 2 is removed. So, G minus 2, what are the values that we get? Now, here we can see that at the second row for the column specified by G minus 2, what we get is all the values to be zeros. Why? Because now 2 is getting eradicated. So, all the links that are reachable from 2 are nullified. Okay, that is why they are all zeros. So, now obviously they are going to put an impact on the calculation part itself. So, what we get at 0.2140. Okay. Now, to find out the drop in coverage, a simple calculation, and we find that there is a 39.72% drop in the communication coverage or information coverage if node 2 is removed, which seems to be a quite important loss in the network. Okay. So, this type of interpretations can be drawn out of centrality measures. Now, another one is cross-clique centrality. What happens in cross-clique centrality is we are interested to find those nodes that are having important connections. Now, important connections could be in form of say a person who is knowing an entire community. A person may be knowing some relevant group of people, or maybe they are connected to some important say research community, etc. Okay. So, what happens? Such nodes, they act as link. Okay. So, this is much closely related to betweenness as well, but in betweenness what happens? Those nodes are they act like bridges, because more often we might be crossing those nodes. But in cross-clique centrality, maybe those nodes are not traversed very often, but they act as like gateway relative to a particular community. Maybe these communities can be in variety of sizes, that is, the importance of the community may vary from low to high. So, in this, a node will have a higher clique centrality or cross-clique centrality, also known as clique overlap centrality. It interprets to be the spreader of disease in socially communicating community graphs. In social communities, people are like meeting, they are speaking with each other, sharing their thoughts, etc. So, if some person is very relevant and he might be a member of some bigger communities or some very important communities where people are coming, and they might also have some link to some more bigger communities. Okay. If we are talking in context of say computer networks, these can be like close authorities or hubs like communities where the information or mining process is being carried out, maybe say for example the workstations or important substations where important information mining is being going on. If some virus reaches those workstation, then what happens? There is a major loss of data. Okay. So, in another context, it can be the initiator of information to facilitate better propagation among other nodes in the network. Maybe like the companies are launching products or some policies, etc. Now, how they should like strategize their business decisions so that to get more and more profit from propagandas and etc., from pamphlet spreading, etc. So, what they do, they choose who are the main initiators of information. That is, if information or message is given to a particular node, then what is the like possibility that that person is connected to maybe some bigger community, maybe knowing some better person or like close structures, infrastructures, etc. So, what happens? Those nodes regarded as initiators are chosen. And again, in context of networking, say for example, when choosing cluster heads in a closely formed clusters. So, these clusters head will be what? They will be lying in a very close distance with respect to each other. So, their reachability might be good, or they might have good betweenness, good measure of connectivity, then such nodes, they get selected as cluster heads, okay, and since they have a good reachability, they can like take the information and they can pass on it, carry forward it to some other maybe base station or other relay to other neighboring cluster heads, etc. So this can be taken as a like criteria for choosing cluster heads or some nodes that can relay the data to a bigger community or a bigger cluster, etc. Okay. And what else? It can be a link to popular community, yes, of course, or a community, or it can be some layer that is upper in the hierarchy. Okay, hierarchy are found everywhere for better organization of data or for better communication of messages, right? Now, and just to recall that cliques are what they are subgraphs in which all the nodes are tied to each other in a strong manner. That is, each node are tied to each other, they are linked with each other. That is what a strong community is. Okay, and when the click over centrality is maximum for a node, it explains that the number of click to which the node belongs may be more in relative to other nodes in the network. Now, let's come to the complex graphs, starting with hypergraph. We know the standard definition of the graph. What happens in standard definition? The simple graph, they don't have any multi-links. They mostly what they do, they connect two nodes at a time. Not more than two nodes can be connected by an edge. We cannot visualize this fact. Okay. Now, with the help of hypergraphs, we'll see that how a single link can be used for connecting more than two vertices. It may also happen in this manner that all the nodes in the graph are connected by a single edge. Okay. So let's see. First, starting with its mathematical description. Mathematically, say a hypergraph, since it's a graph, so it will have a vertex set and an edge set. Okay, and they are mostly used for building transportation networks or like communication networks, drafting social connections, etc. Where most of the time we need some edges, some link, or some special link, so that we can connect two or more entities, maybe people or stations or some wireless devices or wired workstations, etc. into one. Okay. So here again, vertex set will be same as we had in the simple graph or the standard graph, and the vertex means what? It is either real life objects or they are mostly known as nodes. Okay. So say we have n vertices running from V1 to Vn. Okay, and the cardinality, that is the total number of vertices in that particular set V, is equal to n. Then we have the edge set, which is also better known as relations and links, and here we have any number of edges. It depends upon the number of vertices that we have and they are getting connected to. Okay. Now, what are the important constraints that we have here? Since this is a standard hypergraph, so no loops, no self loops, okay, no multi-links. But what happens to the fourth criteria? Earlier, it was E of I, the cardinality of each edge set was strictly equal to 2. Okay, it cannot be 0, 1 or more than 2. It was exactly equal to 2. But now we can see that this is less than equal to n. This specifies n vertex connectivity. That is, now a single edge can be used to connect more than one vertices. Let's see how. Take this example. Now, what happens here is you can see that rather than having a single line drawn, there it's like a cluster or it's like a irregular shape that you can see. But this ABC, this comes under one particular edge, say E1. Okay, BD, they comes under a particular edge set, say E2. Okay, like that. Now, there can be some edges, since they are a collection of nodes where the nodes can be more than 2. So there can be some hyper edges, since these edges are special, so we call it hyper edges or hyperlinks. Okay, so there might be some edges that are overlapping with some other edges. They might be entirely overlapping or partially overlapping. As we can see that B and D, it's overlapped with ABC edge and DEFG edge. Okay, so it's partially overlapped. And in case of a simple graph, what we can see is ABC is the vertex set and edge set. There are 4 edges and they are all strictly in pair of 2. But in hypergraph, we can see that in edge set, there are edges with 3 and 4 vertices. Okay, so this will help you to give an insight of what hypergraphs exactly look like. Okay, now going forward, since we have in case of standard graphs directivity. Okay, directivity means that it shows the direction of flow, from where the message has got initiated and where it has to reach, something like that. Okay, so since these are standard graphs, so they should have another directivity version. So this is what directed hypergraphs are. In this again we have hyper edges, but these are directed hyper edges. Mathematically speaking, if the standard hypergraphs are having directed hyper edges, okay, then we call that that particular graph to be a directed hypergraph. For a hypergraph to be directed, then it should have at least one directed hyperlink. Okay, but it's not stopping here. It's also having something called tail set and a edge set. Okay, now let's say in the example here, the edge is divided into 2 disjoint sets. Remember that we have studied about bipartite graph. Okay, it's very similar to that, as you see in the example. We have 2 subsets over here. They are disjoint, tail set and the head set. If we take up an arrow, the tail part, it will be the tail set, and the head of the arrow, wherever the head of the arrow is pointing, that is our head set, denoted by HEX. Okay. Now you can see, you can just map your concept with a bipartite graph that we have already studied. In tail set, none of the vertex are getting connected. They are connected to the other vertices that are lying in the, say, other set, the head set. Okay. Now what could be the interpretation out of this? One way of saying is there are 6 places. Say if we are taking up transportation network into consideration, then there is 5 places, 1, 2, 3, 4 and 5. And what happens, these places are connected with a particular edge. Okay, and this edge is designated by E1. This is the edge. Now what this directivity relates, it means that 1 and 2 are the places that are not linked with each other, but there is a common road that ends up to 5, 4 and 3. These are the places that if a person is starting from 1 and 2 can reach. Okay. And say for example, if we are taking like a social network graph, then what happens? There might be 2 friends, 1 and 2. They might not be knowing each other, but they have common friends, 4, 5 and 3. And with these friends, they might be sharing some particular video. Maybe 1 is sharing a particular video and 2 is also sharing that particular video unknown to each other. Okay. And if we are say interested to store the details of incidence matrix, then what happens? We take the normal incidence matrix. And remember that incidence matrix is what? It's a 2-dimensional matrix in which one side we have the number of vertices and the other side we have the edges. And if a vertex is lying incident on say some edge is linked with a vertex, then for that particular cell we'll put a 1. If it is not there, if that particular say edge is not containing some vertices, then the respective cell will get 0 value. Okay. But in case of directed hypergraph, we have one more value, that is -1. Okay, so -1 is for those vertex that are lying in the tail set of that edge, and +1 is for those vertices they are lying on the head set of the particular edge, say any edge, say EI. Okay, so this way incidence matrix can get constructed, and it's a very convenient way to store the details of a directed hypergraph. Okay. Now moving on to one more category, that is multigraphs. Okay. Now after studying multigraph, you will know that all these hypergraphs, multigraphs, standard graphs, they can be collaborated to to grow some new type of graphs. Say we can have some hypergraphs with multi-links. So they will become directed hypergraph with multiple links. So they are multigraph as well as hypergraphs altogether. Okay, so these are all the basic categories and concepts that we are studying, but when it comes to real life applicability is like in form of they are all complex forms, like 2 or 3 forms or categories can be merged into to get a new form of a graph. Okay. So in multigraph, what happens in relation to the standard graph, as we know that there are n vertices and some n number of edges, and this is the family that the edge set lies to. And as in figure 1, you can see that we have taken a very simple graph in the example, and the adjacency matrix, this is adjacency matrix because it's a V cross V matrix, right? Means we have vertices on both the row and the column part, as opposed to the incidence matrix where we have only at the one side we have the vertex set and the other side the edges are there. Okay, this is the only difference, and these are the two graphs, these are two matrix based storage available for storing the details of a network model in form of graph. Okay. Now what happens in multigraph? Say for example, we have changed figure 1 a little, we have modified it, and now 1 and 2 are linked with 3 links. Okay, so since there is a redundancy in the number of links, we call it a graph with multiple edges incident on a particular pair of vertices, or we call it a multigraph. So any standard graph or any graph, be it hypergraph or standard graph, any graph, if any type of graph is having at least one more edge, a redundant edge between the existing pair of vertex, then that type of graph will be termed as a multigraph. Okay. And here what happens in an element of V cross V, that is the same adjacent matrix, in this an element of V cross V, if it appears more than once, then it is a multigraph category. Okay. And you can see that its storage in the figure, it's also a little different, right? Normally it would be like a simple 2D representation, but here say 1 and 2, 1 and 1 is not linked with itself, so it's 0. 1 and 2 in the shaded part, you can see that there are 3 ones. Okay, 3 ones means there are 3 edges and the weight by default it's 1. Say for example, we have taken multigraph with weights, then if some of these 3 out of these 3 edges, if some of the links had say 10 or 12 weightage, then you can just simply put it in place of 1, you can put 10, 12 like that. Okay, so it's a very easy, a very convenient way. If we talk in terms of data structures, then for storing the detail of 1 and 2, the link details between the node 1 and 2, what we do, we just create a linked list with 3 nodes or a simple array with 3 cells. Okay, that's it. So another concept that we need to know with context to multigraphs is that if there is a multigraph in which no element of V cross V, that is the adjacent matrix, appears more than p times, then we call it a p graph or a p multigraph. So if somewhere you find there is a 3 graph or 4 graph, it means that that term is in context with the multi-graph only. Now some examples, it will make your concept clear. Order is a what? This is again another new term. It is basically the cardinality of the vertex set. Okay. So if we have taken the first example, you can see that it's a 3 graph of order 4. Since we have 4 vertices A, B, C and D, so order is 4, and 3 graph, it means that how many edges there are between a particular pair of vertex. It's 3, as you can see that between A and B, this is maximum 3. Between B and B also there are 2 self loops, but since it's 2, 3 is more than 2. Again between C and D, we have from C to D and D to C. So these 2 are like unique edges, they are not multi edges. Okay. Between A and B, what happens? All the 3 edges are running from A towards B. So they are redundant edges. So they are counted as 3 multilinks. So this is a 3 graph. And what happens to the next example? We can clearly see that there are 2 links between A and B. Okay, there are 6 vertices, so order is 6, that's clear. But the graph is one graph. One graph means that it's not a multi-graph, right? So it's just a directed graph. So what happens between the vertices A and B, though we have 2 links, but since their directivity is unique, so the graph will be one graph, that is, it's not a multi-graph. Okay, the first example is a multi-graph with maximum of 3 entries, and the second example is not a multi-graph because it's one graph, as there are no links associated with any existing pair of vertices that are repeated. Okay. Now to start with random graphs. Random graphs are those in which the links are randomly formed. These are very interesting graphs, and they are like important for simulating graphs that range over 100 vertices or maybe thousands of real-time nodes to study the performance of large-scale networks, or say for example performance could be in terms of what type of delay that is encountered, or maybe any other kind of, say, throughput is involved if the number of nodes increase, or if the number of links get denser, is there any impact on the throughput, or maybe if you are talking in terms of some electronic devices, networked electronic devices, then if there is some energy drop or some coverage drop that we can study. Okay, so shortly we will start a lecture on random graphs. Thank you. Welcome viewers. On our lecture on random graphs, we start with what is the significance of taking randomness in the first place. Okay, so when we are taking randomness into the modeling, it is providing a hypothetical support to know that what type of impact randomness in links or randomness in number of nodes put on. Okay, so this actually help in representing the complex networks in a more realistic manner, right? Because in real life, what happens, there are a huge number of people, if we talk in context of social network, or even say for example we are taking computer networks into our example, and there might be for example for tracking example or some monitoring instance, some wildlife is going to be monitored. So thousands of nodes, thousands of electronic devices operating wirelessly are dropped, they are spread out in a huge area. So we normally take up the applications where large number of nodes are taken into consideration. So to understand that what impact the huge number of nodes or the dynamically changing link between any pair of node puts on the entire networked graph. Now, for this, indeed, if we are just starting up with the hardware, that it will become very difficult to analyze the performance. So, performance has to be analyzed before the actual implementation is laid out. Okay, so for that, that's why we study the models. Okay, since a network, previously also it has been told that networks are what they are real time, real time cases, and graphs are what they are normally modeling the network concepts, so that even before the network is laid out, we can on the backend part we can check out that whether if this particular network in any domain, in any cross disciplinary domains, if such network is laid out, whether it will be a successful attempt or not. So for that we first do it on graphs for lesser number of nodes. If we are moving to higher, we are scaling up the number of nodes, we go to random graphs, etc. And the main purpose is to study the impact on the performance part. Okay, so model here that we take up, the random model, it enables us to derive certain properties. Let us see what type of properties. It is used for predicting the outcomes under certain constraints. Since this is model, model is what? It's simple, like a black box. So besides giving the input and predicting the output or the outcome, we can also put some constraints, some restrictions, that within this particular time frame or particular values of some variables, or we have constrained the number of variables, etc. So under some constraint, what the outcome will we actually face. Next will be obviously the appropriate analysis of the proposed model, and to establish correctness in the representation of the real world network. Yes, it's very important, because establishing reliability, to have reliability on the model, it has to be very correct. So to take up this correctness issue, what we do, we normally model it a number of times to get an appropriate model, a model that is suitable from a certain context for a particular domain or some discipline, etc. So now random graphs also have like a variety of versions. There are so many types, etc. Just to start with, we take up the very benchmark model, the random graphs, and they are known as Erdős-Renyi random graphs, or in short they are known as ER graphs. Okay, so with ER graphs we will try to model huge number of nodes that a network can have, and large complex nodes with denser links or sparse links. And what else? Besides the number of nodes and number of links, we are also interested to know the dynamism in the network. That is, whether the nodes, those nodes may be obviously the real life objects or any other entity, etc. Whether these entities, they are coming, they are entering the system, and are they going to stay in the system for its entire functional lifetime, or they will get vanish within that lifetime before it expires. Okay, so this is one important constraint. It means that, let's take up an example of a wireless network of nodes, and these nodes are mostly battery operated. So whenever it engages into tasks, their battery gets drained out, and certain stage might come that the node entirely gets drained out of energy, and the network administrators call them as dead nodes. Okay, so those nodes simply get vanish out of the map of the network. Okay, so the nodes get vanished even before the network, for what purpose that network was laid out, that purpose was not completed, but before its operational lifetime expires, the nodes are getting dead. So this type of concepts involve dynamism, they produce dynamism in the network. Okay. Even if, say for example, there is mobility, the people are moving with wireless devices, say for example, and since they are moving towards some workstation and moving out of the workstation, so that way the link will change. Okay, we have also seen that whenever we are under the coverage of some mobile station, say, then what happens, we might be getting a very good antenna strength, or if you are moving out maybe in some farming areas and all those, or some hilly regions, etc., then we find that the antenna strength gets dropped. Okay, so the link, the quality of the link, the presence or absence of the link is also going to determine some kind of dynamism in the network. Okay. Now, before studying the random graph, how it works, what are its properties and other constraints, we need to know the assumptions. So here there are n disconnected nodes in the network. We start like that. No nodes are connected to each other, okay, initially at stage 0. Then what happens? An undirected graph is formed with nodes connecting independently in a random manner. Random manner means what? Random manner means that for link formation between a particular pair of node has nothing to do with the link formation with any other pair of nodes in the network. Okay. They are independently being formed, and they can be formed at any time. Okay, say instant of time. Now what happens? A node will try to have links, that is it will try to have edges with the rest of the network having n minus 1 nodes. So a particular node can have how many neighbors? At most they can have n minus 1 neighbors by linking with n minus 1 edges with them. What else? The attempt, the link formation attempt, that is a particular node wants to connect to another node. So it eventually what it does, it requests. So that this link formation request may be a success or a failure. Okay. So if it is a success, we call it the success with some probability p. Okay. And since the success probability is p, then very clearly the failure probability will be 1 minus p. And if we take this entire process, the random process, to be governed by a distribution, say binary distribution, which is a very simple one here and very appropriate in this case. So if you are taking binomial distribution to give the probability that a node possesses a particular degree means a node is getting connected or a node is forming link with d number of other nodes in the network. Okay. So if this is the case, then what happens? The formula that is shown here, this formula, this binomial distribution formula is going to give you the probability of success, that yes, a node, a particular node can have a d number of links by following the binomial distribution formula. Okay. Now next is what is this parameter p that is there in the study. P is what, as you can see in this formula, the binomial distribution formula, P is what is the probability of success, and how this probability of success could be designed. There can be different ways. A very crude way could be flipping up of an unbiased coin. Okay. Say if in a social network a person wants to make friendship with other person in a network, then if he starts with flipping a coin, flips a coin, if he gets a head for a particular person, it will send a friend request randomly, just like that. Okay. So in this way also the network can start forming, the network can start growing from its initial phase to a very complicated phase with a large number of links. Okay. So flipping of unbiased coin can be one. If head, then form the link. If tail, then no formation of link. Simple. It's a very crude way. Others can be, it can be a outcome of some distribution function. There are several mathematical distribution functions available. You can take up any distribution function and with providing a random seed, you can just take the value and with that probability the link is formed or it is not. Even it can be a little more better by setting a threshold function. For forming a link, say for example, we have taken the outcome of a distribution function or flipping up of a coin. These are like random experiments. Okay, so say for example, we have continued these random experiments for a certain number of trials, maybe n trials, and after the n number of trials, we are checking out what is the probability, the aggregated probability. If the aggregated value is more than some threshold, then the link is formed. If it's lower than the threshold, then the link is not formed. So these are some ways by which we can model the probability of success. Okay, we can define the probability of success. And then what is the approximation for largely dense network? If we are taking very large networks, and since the degree distribution here we have taken to be binomial, right, for the probability of success and failure. So this binomial distribution for large n, that is for large number of nodes, and a small p, there is a very small probability of success, which means that not very dense network. For that case, binomial formulation is often approximated with the help of Poisson distribution. This is a very general concept. Okay, so with this formula, you can check out and approximate the binomial to Poisson distribution. Next, now the random graph with degrees that are Poisson distributed. Now we are talking about bigger graphs. So no binomial distribution. From now we take a Poisson distributed degree distribution. Okay. Now here our ER graph, that is the Dor-Shreni random graph, it becomes Poisson random graph. Okay. So this is ER based on Poisson distribution, and it's a random graph. That's why ER Poisson random graph, also known as Bolobash network configuration. And the expected degree here is p into n minus 1. For a large number of nodes, this is often approximated to NP. Okay. Now, another term that is associated with random graphs is the ER based on giant components, also known as GC. These are the largest components in the network. We know what a component is. If a graph is having more than one component, then we call it a disconnected graph. If it is having exactly one component, it's connected graph. In more realistic examples, we normally have more than one components. Okay. So whatever is the size of the largest component, it becomes our giant component. And what's the behavior of the nodes in that particular giant component, it becomes say a talk of interest in a close community, that okay, this particular community is engaged in this trend, or these researchers are doing experiments, or they are doing a certain kind of technological experiments, etc., on this particular technology, then it becomes a trend. So the GC is something that like it lays out some trends, or they are a community of very importance. Okay. So GC later on we will see that how to optimize, how to calculate the size of GC, and the size of GC will also determine the nature of the graph, with what rate it is growing, the graph is growing, or it is a stable graph, etc. Okay. Later on we will see. And another important property that GC has is that GC will always occupy finite number of nodes. It's a finite fraction. Okay. And this finiteness property will hold even if the network model, that is a graph, tends to grow infinitely, because all the nodes are not going to get connected, because that is not practical. Because a person, even if in social network, a person, there are so many people on the Facebook, but a person is not connected to everyone on the Facebook, right? So there might be millions and millions of nodes on the Facebook, but when we check out for the links, they are very, very sparse. Okay. Same for any, take up any real life domain, the same is the case. There may be a large number of nodes, there can be large number of say places in the transportation network, large number of stations, wireless stations or wired backbone stations, but they are all not linked with each other, which means that they are not strongly connected. There is a sparse connectivity, and this is what random network model is basically based on. Okay, right? This is the basic concept behind this model that we are studying. Now let's start with the degree distribution part. Degree distribution, why it is important? Because it helps to know the hubs, which are the hubs of information from which messages can start initiating or traveling, etc. Or it can also help to understand the geodesic measures. Geodesic are what? They are shortest paths. The number of shortest paths you can easily find out by calculating the number of geodesics, and it will also determine whether the network is evenly distributed or it is at some places it's very like dense, creating some hotspot areas, etc. Now, to understand this distribution more, let's do know this theorem. This theorem is very important, and for this assumption is that the links are dense enough such that the network is assumed to be connected. It should not be very dense, but it should be dense at least to get it connected, and for that the criteria is degree of a node n is greater than or equal to some constant multiplied by log n. Okay. Now, what is this constant 1 plus epsilon? It shows that this constant is strictly greater than 1, because 1 is already added. So, and epsilon is a positive value. Okay. So, this constant is strictly positive. And the theorem goes that if you are taking up APL, that is average path length or average geodesic, or diameter into consideration, then this value is this average path length or diameter, they are going to get proportional to log n by log d. Log n, the total number of nodes in the network, divided by log d, average degree that a node will have. Even from this particular theorem, another phenomena that got evolved is known as 6-degree separation. This is mostly in context of social networks, so we are not going in that direction, but still 6-degree separation, what happens? It says that any person in the planet, they can be reachable in 6 steps, provided that proper or logical path is taken towards the particular destination. Now, the isolation probability. We have the random graph, we have a lot number of nodes, we know how to randomly form the links, we know about the degree distribution. Okay. Now, we are inquisitive to know that what is the probability that a particular node is isolated from the graph, because the nodes that are isolated are also of importance, right. So, for this what we do, we take up this formula which is very evident from the last model that we were studying. Here what happens, the ED, that is the expected degree or the average degree of the graph, is greater than or equal to 1 plus epsilon log n, again the same formula. And this threshold is what? Whenever we are defining this threshold, it means that it is the threshold of having each node to have some links. Okay. So, this is in some sense we can say that the criteria for a node to get connected. Okay. And beyond this threshold, there are chances that we will have some disconnected components. There is a other way of saying. Okay. So, if we write it in a different way, we can say that the one essential condition for this is the expected degree equal to r plus log n. And for denser network, we already know that expected degree is what? It is p into n minus 1, and for larger n, if we take out one node from it, it will not matter. So, it is almost equal to Pn or Np, whatever. So, we have these two formulas. Okay. Now, if we relate these two formulas with the assumption that link formation are entirely random and they are independent of each other, Okay, what happens? We are just equate it, and we can find out that the probability of absence of any link would be 1 minus p, because remember that success for link formation success is p. So, the failure will be 1 minus p, and when we equate these two equations 2 and 3, because they are having they are the formulation for the same average degree. Okay, so r plus log n can be equated to p multiplied by n minus 1, and we can get a formula that is specified in equation 4, that p is r plus log n by n minus 1. Okay, so this is the value of the probability of success in another way. And if we want to calculate the probability that a particular node I has got isolated from this large randomly formed network, then how to calculate it? It will be nothing but 1 minus p to the power n minus 1. Okay, it comes out from this conception that p is a probability of success, right? A node has got connected with one neighbor. What is the success probability? P. It has not got connected, the probability will be 1 minus p. So, if we are interested to know that a particular node n is not connected to one node in the network, any one node, then the probability would be 1 minus p. Since we are talking about n minus 1 nodes, because the maximum possibility that a node n can get connected to is n minus 1, leaving itself out from the entire network. Okay, so this will be 1 minus p, that is a failure probability raised to the power n minus 1. Okay, and we know the value of p from equation 4. So, just put it and you get the isolation probability. It is as simple as that. Okay, so given any network with large number of nodes, you can find out that depending upon the probability of success, what is the probability that some nodes will be left out. Okay, so and here in equation 6, a little approximation is applied relative to equation 5 that you have seen. P iso, that is isolated probability, is this, but since this is a very complicated, it is complicated looking, we can just apply Taylor series approximation, and we can find that it is e to the power minus r by the total number of nodes n. This is with respect to one node. Now, if we want to calculate for the entire network, what we will do? We will just sum up the values of the isolation probabilities. Okay, and we sum it up, we just get that e to the power minus r is the isolation probability. Now, some interpretations, quick interpretations, that if r is equal to ed minus log n and this value tends to infinity, it means that expected number of isolated nodes are going to 0, which means that the graph is getting towards more and more towards connectivity, that it is getting connected, okay, densely connected. It also there is one more interpretation that it provides an instance of well connected network, and as r tends toward minus infinity on the reverse direction, it means that average number of isolated nodes are getting increasing, they are just the amount is increasing infinitely. Okay, so these are the interpretations. Now, the giant component. We know the giant component is the size of the largest component in the network, and say we assume that the fraction of the nodes that are within the giant component, within this largest component, is say q. Okay. Now, considering that in the entire random network of n number of nodes, we have taken any one node, we have randomly picked up any one node, and what is the chance that it will be in the giant component? The chance will be q, because q is showing the fraction of nodes in the giant component. Say the giant component comprises of 60% of the total nodes in the network. Q will be what? Q is nothing but 0.6. So, what is the probability that I take up any node at random, and I want to know that what is the probability that this particular node lies in the giant component will be nothing but 0.6. Okay. So, this is how it is done. Next, what is the chance that the node n is outside GC? it will be nothing but the probability 1 minus q, because with probability q it is within the giant component, with 1 minus q it will be outside the giant component. Okay, and the chance that all these nodes are outside GC would be same as saying if a particular node is having some neighbors and all those neighbors are outside GC. Okay, then it will be what? The failure, the 1 minus q, that is they are not a part of the giant component, raised to the power the number of the neighbors it is having. Okay, say the number of nodes, the neighbors that are having is d, where d is the degree, which is the measure of the number of neighbors a node has. Okay, so it will be simple 1 minus q raised to the power d. Okay, then what we have done is PD. It is the chance that a node n has d neighbors. Since we are dealing with the Poisson random graphs, so what happens, we have just taken the formula as 1 minus q to the power d, okay, that is previously calculated in equation 9, and then PD is the distribution, so we have just multiplied it, and we have equated it with 1 minus q, because you can see that equations 8 and 9, they are the two different ways of saying the same thing. So we can equate it. So 1 minus q will be equal to a summation of 1 minus q to the power d for all the neighbors of that particular node multiplied by PD. Okay, and we get this formula that is specified by 13 by, obviously since we are dealing with a Poisson distribution now, so we have applied nothing but the Poisson formula. Okay, and the average degree that is specified by lambda, and average degree is NP, previously told. Okay, so just plug in the value lambda equal to NP into equation 12 and we get equation 14. Okay, now since equation 14 has got a little complicated, again Taylor approximation is used. Taylor approximation is nothing, it's e to the power x expansion 1 plus x square by 2 factorial, etc. So what happens here is we have taken x to be what? This entire part, okay, in equation 14, and minus, and this part is what? 1 minus q multiplied by NP. Okay, so and NP was thing that was already out of the formulation, and we get equation 15 out of it. Just take log on both sides, do a little calculation, you will end up with the average, a relation between the average degree and the size of the giant component. So if you plot this, you get a curve that is shown here in the figure, that as the number of neighbors of a particular node increases, the giant component size also tend to increase. So for this lecture, it's this much for now. Thank you.
Thank you, ma'am. Thank you so very much. Dear friends, for any suggestions or any kind of question which you would like to ask, then you can definitely contact us through our email ID. Our email ID is info.cc@nic.in. We would be meeting again and would be discussing more on the particular series. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.